In a previous video, we looked at the idea of the inductor and how when inductors are energized, they take the shape of a growth curve like we see on the screen here. And so rather than a sudden increase of current when we switch an inductor on or a linear straight line increase, what we actually see is this curved shape. We get a fairly rapid increase at first and then leveling off over time. One other thing to consider is that because we're creating a current in an inductor, a voltage is also created, which is created in the opposite direction to that of the supply. This is something called back EMF, and it's essentially the inductor trying to resist this sudden increase in current. It creates a voltage that opposes the voltage of the supply. In some inductors, very large inductors such as motors, we can see very large back EMFs created when we switch them on. You might notice, for instance, when you switch on the vacuum cleaner in the house or an electric shower, the lights dim for a moment, and that's this back EMF in effect. The switching on of that motor or inductive load creates a back EMF, a voltage that opposes the supply, and this can have some very serious effect in some instances. One thing we're going to do in this video is try and calculate back EMF, and we can do that by using the formula EMF equals minus L di by dt. Let's have a look at what some of the terms in this formula mean. We know that L represents inductance. We know that I represents current and T represents time, as we've got in our graph here, a graph of I against T. But when we say di by dt, we're actually referring to the change in I over the change in T. Now, if we're familiar with calculus and differentiation, we can actually differentiate functions of current in order to get the EMF, but we're going to take a simpler approach in this video. The rate of change of current is always changing, and what I mean by that is, at the start we have a very steep incline to our growth curve. Later on, this isn't quite so steep, and by the end, we're pretty much level. There's no change in current over time. What I'm going to do is I'm going to take an approximation, and what I mean by that is, for this first sort of section of the diagram, I'm going to imagine that we can think of this as a straight line from there to about there, say. So our calculations aren't going to be perfect, but in this instance we'll get a pretty rough idea of what the back EMF will be in this instance. Let's say, for example's sake, that for my little section that I've outlined here, we see a change of current of 0.2 amps. So we've increased from 0 to 0.2 amps, and we've done this in a time of 1 millisecond. Let's also say that my inductor has a value of 50 millihenries. So let's apply this to the formula, because we can now say that the formula for EMF is going to be equal to minus L, which in this case is minus 50 times 10 to the minus 3, multiplied by di by dt, the change in I over the change in T. Well, I in this case is changed by 0.2 and T has changed by 1 millisecond, or 1 times 10 to the minus 3. And if I calculate that, I get an answer of minus 10 volts. So in this case, when I switch this inductor on, in the first millisecond, we're going to see somewhere around minus 10 volts being created in back EMF. So this isn't a perfect solution to calculating back EMF, but I hope that it's a reasonable start and a good approximation to calculating back EMF in an inductor, given the type of growth curve that we've seen on the screen here.